Cooling system loads are heavier and operating demands are greater, but temperature control in today's engines is still basically concerned with two things: bringing the cold engine up to operating temperature evenly and quickly, and maintaining constant operating temperature so the engine will not run too hot or too cool. Along with these basic functions, the engine cooling system is also involved in controlling automatic transmission fluid temperature and in operating temperature-sensitive engine and emission control units. So, to better understand how it all goes together, let's begin with a brief trip through a typical engine cooling system. In our basic system, we have passages in the engine block and cylinder heads where the coolant picks up heat generated by engine operation, a belt-driven pump and fan to circulate coolant and air, a thermostat to control coolant flow, and a radiator where the coolant passes the heat to outside air. Coolant from the pump picks up heat as it flows through the cylinder wall passages, and then through cylinder head and manifold passages on its way to the thermostat outlet housing. When the coolant is below normal operating temperature, the thermostat remains closed, blocking direct flow to the radiator. As a result, the coolant takes an alternate path through a bypass hose or passage to the inlet side of the pump and recirculates within the engine to help it warm up evenly and quickly. As the engine nears operating temperature, the thermostat begins to open and heated coolant then passes into the top tank of the radiator and flows downward, passing heat to the radiator core tubes. At the same time, the air passing through the cooling fins on the outside of the tubes carries away much of the heat to reduce the coolant temperature. Leaving the core tubes, the coolant flows out of the bottom tank through the lower hose on its way to the pump inlet for another trip through the system. When coolant temperature drops below the minimum for efficient engine operation, thermostat action reduces flow through the radiator to keep the engine temperature constant. On automatic transmission models, a transmission fluid cooler is installed in the radiator bottom tank, and in maximum cooling installations, an auxiliary fluid cooler is connected in series with the tank cooler. The importance of using the recommended antifreeze coolant mixture can be seen in the fact that today's engine cooling systems are designed to take full advantage of the relatively high boiling point of this mixture. As you probably know, the coolant inhibitors, which retard rust and corrosion and prevent foaming during circulation, are gradually used up by the effects of engine heat and possible exhaust gas seepage. However, except for the use of emulsifying oil to retard radiator core corrosion, it is not advisable to add inhibitors separately to stretch out the life of the antifreeze coolant mixture. The safest and best procedure is to completely replace the used mixture at recommended intervals. Coolant pumps come with different impellers, so be sure the impeller of a new replacement pump matches the old one. Substituting a large impeller pump for a small one will result in excessive pressure, which can damage the system. Substituting a small impeller pump for a large one produces an opposite result. Here, the reduced pump output cannot circulate enough coolant to keep the engine from overheating, especially during hot weather operation. In all of our 75 passenger car engines, the thermostat begins opening at 195 degrees and opens fully at 215 degrees. Thermostat testing is covered in detail in the service manual. However, in brief, the coolant temperature is taken at the radiator filler neck with the engine fully warmed up to check thermostat operation. The top of the pressure vent radiator cap is now made of corrosion-resistant stainless steel. The top also swivels, so it can be turned without scrubbing the seals and shortening their life. The radiator cap seals and the vent valve must be in good condition to operate properly. You can use the radiator cap tester to pressure test the cap and the cooling system. Operation of the pressure vent radiator cap is slightly different from some earlier models because the radiator top tank is now kept completely filled by the coolant reserve feature. Here, the cap vent valve is designed to allow expanding coolant to pass out through the overflow tube into the coolant reserve tank. When the force of expansion flow increases enough to lift the vent valve, it closes, allowing system pressure to build up. When pressure in the cooling system builds up more than 16 pounds, it unseats the cap relief valve to maintain the rated pressure. Coolant forced out when the relief valve opens also flows into the coolant reserve tank. When the system cools down, the coolant contracts, and the backflow which results pulls the vent valve open as the overflow is drawn back into the radiator. At least 1 quart of reserve coolant must remain in the tank to cover the open end of the overflow tube so air will not enter the system. Checking the coolant reserve system operation is easy. The level in the reserve tank should drop the same amount that is drained out at the radiator drain cock. Air leaks at the overflow hose connections or radiator cap will allow the original amount of coolant to remain in the tank. 3 different basic fans are used on our 75 passenger car engines. You'll find 4, 5, and 7-blade fans, depending on the model. In some systems, the fan works full time. In others, it coasts when the cooling system does not need it. Some of the 5 and 7-blade fans have flexible blades which flatten and change their pitch at high engine speeds. As the blades flatten, mainly due to centrifugal force, the fan turns more easily, reducing fan noise and engine load. To do the same job, some light truck fans have a fluid coupling type fan drive which slips automatically at high engine speeds. A fluid coupling fan drive is also used on some passenger vehicles, but this type of coupling is controlled by a thermostatic coil-operated valve inside the drive unit. When the thermostatic coil is cold, the valve orifice remains closed, preventing silicone fluid from entering the coupling section of the drive, so the fan turns at less than pulley speed. As the radiator warms up, airflow through the core heats the thermostatic coil, which opens the valve orifice. The fan then runs at pulley speed until the coupling slips, limiting top fan speed. When starting in cold weather, the coupling may turn the fan at pulley speed temporarily because the coupling fluid is thick. And remember that some heavy-duty cooling system fan drives have an idle lockup feature, which turns the fan full-time at low speeds regardless of system temperature. We can check the thermostatic fan drive coupling operation by noting the clutch cut-in and cut-out temperatures. To make this check, we first insert the stem of a dial thermometer through a stem-size hole drilled in the top center of the fan shroud between the fan and the radiator core, clear of the fan. Airflow through the radiator is blocked off with a plastic sheet in front of the air conditioning condenser or the radiator. We also need a tachometer for checking engine speed. Make sure the air conditioning system is shut off to prevent excessive compressor head pressures during the test. Then, start the engine and run it at 2400 RPM for the test. The fan should turn at less than pulley speed during the warm-up. The drive should cut in and speed up the fan at or before the temperature reading reaches 190 degrees. At 190 degrees, remove the plastic sheet to restore radiator airflow. The temperature reading should quickly drop 20 degrees or more, and the fan should slow down. The temperature should not exceed 200 degrees during the test. A fan shroud is used with nearly all V8s and some 6s to help the fan draw cooling air more evenly through the radiator core. Without a shroud, the greatest airflow would be through the core area swept by the fan. The coolant pump drive belt, as well as all accessory drive belts, should be in good condition with belt tension properly adjusted to assure satisfactory operation. Both the gauge method and the torque method for adjusting drive belt tension are covered in the service manual, so we won't repeat the procedures here. In any case, do not use pry bar adjustment or attempt to adjust belt tension when the engine is running. Some models have a thermal ignition control valve which temporarily speeds up the engine to prevent overheating at idle or low running speeds. At 225 degrees, the valve routes full manifold vacuum to the distributor vacuum advance unit, advancing the timing to speed up the engine. In most models, the temperature-operated coolant control exhaust gas recirculation valve is located in the top tank of the radiator. Above 75 degrees, this valve opens to allow the exhaust gas recirculation system to operate. The coolant-controlled idle enrichment valve is used on all automatic transmission models to reduce stalling after cold starts. This valve is mounted in the coolant pump housing, in the intake manifold, or in the engine block water jacket, depending on the engine model. When the coolant temperature is below 138 degrees in federal requirement models, or below 86 degrees in California requirement models, the coolant valve permits manifold vacuum to operate the idle enrichment valve in the carburetor. Obviously, there is much more to engine temperature control than we've been able to talk about here. But when you combine this with the detailed information in your service manuals and your own know-how, servicing and troubleshooting problems should unravel quickly.